road, and he's going to tell us about the geometry of 0-2 pairs.
Thank you guys for inviting me here. It's really great to visit AIM again, especially we're so close, so it's kind of fun driving. So my talk today is going to be about the 3 papers that I worked on with a bunch of collaborators over the last year about 0,2 theories, including gauge theories and some non-linear models in 2 dimensions, and their interpretations for the purpose of paradoxical computation potentially. So here's the plan of the talk. For completeness, I will introduce you guys to the notation I'm going to use for 0-2 gauge theories that people usually use in 2 dimensions. And then I will discuss these newly discovered dualities and what's called the triality between different gauge theories fitting the UV that flow to the same IR fixture. And we will do so by using this geometric method by looking at their Higgs branch geometry and using a bunch of mathematical dualities and some physical arguments, we'll be able to realize these dualities geometrically. And for a test of these dualities and trialities, we proposed a theorem about the true chiral spectrum of nonlinear sigma sitting in the IR, and proposed a way of computing these chiral spectrums. And we will see that we will see some surprising results that people wouldn't hope for. For example, 2 phases of a given gauge theory will have different chiral spectrums in terms of their IR geometry, and that's kind of surprising because people thought 2 phases of the same gauge theory would have the same chiral spectrum. But we will see an argument for the mismatch is actually a good thing. And then finally, this is an unfinished paper, the last one. It's coming out in the near future about silver symmetrical localization, and using that to compute exact correlation functions in 0,2 gauge theories in 2 dimensions. So let me start with an introduction to 0,2 gauge theories. The starting point of researching on 0,2 gauge theories in 2 dimensions was started in the 80s because of heterogeneous computation. People argued back then that if you want n equals 1 supersymmetry in your target space physics, then you need at least 0,2 supersymmetry on your worksheet. And since then, people have studied 0,2 supersymmetry extensively. But in the old days, people were kind of focusing on 0,2 gauge theories with abelian gauge groups, because those are the ones which have nice mathematical interpretations as toric varieties or hypersurfaces inside toric varieties. And because they are toric, you can use combinatoric techniques to compute a lot of stuff. And there is a rich story and a rich history along those lines. As I explaining, this is motivated by heterogeneous computation to give you a spectrum of method states on your space-time physics. And there's a deep relation with algebra geometry because of Calabi-Yau hypersurfaces in toric varieties. Also, I want to mention that there's this business called quantum shift cohomology. You might be familiar with what's called quantum cohomology coming out of 2,2 supersymmetric theories in 2 dimensions because of Witten. And it's a deformation of the usual classical cohomology ring on toric variety or generally on Taylor manifold. And if you do a topological twist, a twist to the specific to the quantum filter that defines the quantum cohomology, you will have this deformation introduced by a parameter called quantum parameter. And there's a rigorous mathematical definition of quantum cohomology. And analogously for 0,2 guys, you can define what's called a quantum shift cohomology. But unfortunately, there isn't a general definition for any Taylor manifold and any bundles over them about this quantum shift cohomology. So far, the mathematically rigorous definition is done for deformations of tangent bundles of toric varieties. But from physics point of view, there's no obstruction of doing this for a lot of other spaces. It's a definition of the usual shift cohomology associated to the gauge bound of your 0,2 series. So we'll talk about that in the last. And one particular thing that has been trendy over the last several years is the analysis of 0,2 gauge theory with non-invariant gauge rules. And as I was explaining, in the early days, people were kind of focused on invariant cases because of toric variety and toric structures. Recently, people have been starting to think about non-invariant gauge theories, what's called gauge linear sigma models, on two-dimensional Minkowski space. And along the discoveries of many new phenomena, people have discovered a lot of new dualities between different looking UV gauge theories with non-invariant gauge rules. And there is this interesting thing called triality, which means that you have three different looking gauge theories, but they flow to the same IR fixed point. Of course, these provide new tools for doing heterostring computation because they probably will give you more computation schemes you can use to compute your massless states, so that you might have the hope to find a realistic model for particle physics. So how do we do that? For us, the idea is to study these non-invariant gauge GLSMs with looking at their Higgs branch geometries by solving the determinant F-term equations. And you combine this with the phase structure proposed by Witten many years ago of gauge theories in 2 dimensions. We explore many possible dualities within them by looking at the mathematical identities of different geometries. And of course, you can test these dualities by not just looking at the IR geometries, but also computing a bunch of physically interesting quantities like arguments or like indigenous or to Hooft anomaly matching conditions to test whether the duality is actually true or not. So let me set the stage for the notation of 0,2 series. Usually we use superspace or supermanifold in this case, the flat supermanifold of 0,2 supersymmetry. You have 2 bosonic coordinates and 2 fermionic coordinates. I want to emphasize that I'm on Minkowski space, so I wrote R11 there. This R2 should be R11 too. Because on Minkowski space, you can actually demand reality condition on spinors, so you don't have to double the degree of freedom. For the purpose of later discussion on supersymmetrical rotation, people usually go to Euclidean signature, where you have to complexify your field, so that you have twice the amount of field that you would like. And there things get very tricky. But nonetheless, in both cases, you can still define these 2 super derivatives on the super manifold. They are actually secretly defining two integrable rank 0, 1 totally fermionic bundles on the super manifold. And here are some examples of superfields with 0,2 supersymmetry. You might be familiar with chiral superfields of 2,2 supersymmetry, but it's a misnomer because that chiral superfield of 2,2 comes from chiral superfield of n equals 1 in 4 dimensions. So it's not really chiral in 2 dimensions. Here, the chiral superfield in 0,2 supersymmetry is truly chiral in 2 dimensions because it only has one chirality, the right-moving fermion in this multiplet. So here, in terms of odd coordinates expansion, you have lowest component, which is scalar, and fermionic field, which is the right-moving fermion. Another peculiar superfield of 0,2 supersymmetry is called the Fermi superfield, which is defined by this equation. As you may recall, a chiral superfield is defined by a similar equation, but the right-hand side is 0. For Fermi superfield, you can do something more. You can put a holomorphic, you can put any chiral superfield on the right-hand side. In particular, this E can be a holomorphic function of all the other chiral superfields in your theory, so it can be expanded like this way. So a Fermi superfield provides the interaction terms for 0,2 gauge theories via this E term. So here, this term will generate Yukawa couplings between chiral superfield and Fermi superfield. So this is a special type of superpotential you have in 0,2 supersymmetry. And of course, to do gauge theory, you have to define a vector superfield. A 0,2 vector superfield on the y-Fumino gauge, you have the components like this, where A are the components of the usual bosonic gauge field, and you have left-moving gauginos. Notice that you don't have fermionic, you don't have right-moving gauginos in general 0,2 cases. In some cases which are deformation 2,2, you do have right-moving gauginos, but generically you don't. So a 0,2 vector superfield only has left-moving gauginos inside it, and here big D is auxiliary fields, which by integrating out will give you the D-term equation you can solve to get geometry alone. And of course, as usual, you can define a gauge field strength, which is gauge invariant, by using that vector superfield that we just saw. And this guy only contains physical parameters like the gaugino and the stress tensor, the Yang-Mills tensor F01 in 2 dimensions. And here I define the derivative, gauge covariant derivative as usual, where you have 2 dimensions instead of 4. So using those notations, generically, 0,2 gauge theory in 2 dimensions has these Lagrangian expressions in terms of component fields. So the first one is for the gauge field. So you have the usual Yang-Mills action, and then a kinetic term for gauginos, and the total square for the algebraic field D. So there's no kinetic term for that. And I should apologize for notation abusing, because people usually use lambda for both gaugino and left-moving fermions. So here, these lambdas are gauginos. So those are Yukawa couplings from gauginos and the fields from a chiral multiplier. And notice this term is a square term. That's the term will give you the geometry. And the third line is Lagrangian for Fermi superfield. So here you have a field G squared, which is a auxiliary field, but here you have a E squared. As I was saying, E is a holomorphic function of all the other chiral superfields in your theory, so that's a very interesting term. And here are the Yukawa couplings generated by the E terms. So you have 2 different kind of interactions. This one and that one we usually call G. This J superpotential is corresponding to the usual 2,2 superpotentials. So you have coupling between the left and right moving fermions via this holomorphic function G of other chiral superfields. And finally, you can add what's called a twisted superpotential. And in this case, it's only possible to write down such a D term with I5 parameter.
So what do I and A run over?
Here A is a gauge index. You run over all the indexes of the algebra. But here A is some arbitrary number of J's you want to put in. So J, for a particular A, J is just a holomorphic function of all the other characteristics.
And I runs over.
Right around all possible number of characteristics, it's a flavor index. So whatever the number of chiral superfields or Fermi superfields you have. So here, because as I was explaining, 0,2 gauge theories in 2 dimensions are truly chiral, so you should worry about gauge anomalies. And the usual argument of analyzing gauge anomaly goes through in this case too. So instead of a triangular Feynman diagram, you have to complete in 4 dimensions, you have a loop and 2 dots associated to it. So instead of a 3rd order invariant, you have a 2nd order invariant from your algebra. And there are 2 ways of constructing a 2nd order invariant. The first one is what's called second quadratic Casimir, which is labeled as Cas2 here. And the second way is just use the 1st order Casimir and square it. It's also a 2nd order invariant. And here, by R left, I mean the representation of the left moving fermions. And by R right, I mean the representation of the right moving fermions. So these are the anomaly cancellation conditions. Whatever your field condition is, they have to satisfy these two equations. And one of the major arguments we use, and we prove in our paper, is that this anomaly cancellation condition is actually equivalent to this simple equation in IR, where you do have a geometric interpretation, and the condition is the second Chern character of the gauge bundle have to be the same as the second Chern character of the underlying tangent bundle, the tangent bundle of the underlying space. And it just turns out this is exactly the same as the 0,2 anomaly cancellation for nonlinear sigma models. So this is a very good result, saying that the UV anomaly cancellation is the same as the IR nonlinear sigma model anomaly cancellation. And from Whedon's original work of the interpretation of the IR geometries of this gauge series in two dimensions, we know that the Higgs branch of a UK GLSM has the following structure. First of all, you have a base space, which is usually a hypersurface or a subspace of a Grassmannian, where K will be the rank of the gauge group, which is in this case UK, and N is the number of flavors. And because there are 0, 2, you also have the additional data, which is a holomorphic vector bundle over that base space. And in heterostring communication, this is usually called a gauge bundle. And physicists say that the left-moving fermions couple to this vector bundle, which basically means there are sections of this bundle, fermionic sections. And there are many ways of defining gauge bundles like this in terms of the gauge theory data. But for our purpose, we'll focus on this particular expression in terms of the kernel of this map. Here you define a map, and this is the exact sequence, so the gauge bundle is going to be the kernel of the map. You can also do co-kernel and co-homology of the monad, but this is the simplest case we can consider, and it will be useful for discussing duality. So we'll be seeing a lot of bundles on Grassmannians. And to do that, we'll specialize to a special class of bundles on Grassmannian. Recall that Grassmannian is a homogeneous space, closure space of UN by UK times UN minus K. As such, there's a principal bundle on Grassmannians naturally with fibers being UK times UN minus K. So if the usual story of associated vector bundles goes like, if you choose the representation of the gauge bundle, then you can define a vector bundle on your base space. And here if you choose the representation alpha to be a representation of UK times UN minus K, then the associated vector bundle is going to be called a homogeneous bundle. And if you specialize further, you just choose a non-trivial representation of UK and a trivial representation of the UN minus K factor, then this kind of bundle will be called special homogeneous, and we will label them as O or rho. And the notation follows from this simple example that everybody knows. The line bundles on projective spaces are labeled as O of n, where n is an integer corresponding to the irreducible representation of the U1, because CPNs are defined by U1 H series. So we're just doing a bit more general than that. And beyond that, there's analogous bundle on any Grassmannian. It's analogous to O-1, the topological bundle on projective spaces. And here it's generically called universal subbundle and labeled as S. And the point is that it's defined exactly as the same as O-1 on projective space. You take a point, and the fiber over that point will be the subspace the point represents in Cn. So in this case, this guy is a special homogeneous bundle corresponding to the anti-fundamental representation of UK, just like O-1 has charge -1, which is the anti-fundamental representation of U1. And similarly, you can consider the dual bundle of this guy, which is labeled as S star. So it corresponds to the fundamental representation of UK. So whenever you see your theory has fundamental and anti-fundamental representations, they will contribute a factor like this in the IR. And using products and sums of S and S star, and also their dual bundles, you can produce a huge class of homogeneous vector bundles on the Grassmannian GTN, and we'll be using them a lot later. So to be fully consistent, I should say a few words about representation of UK algebra. Generally, people think of UK algebra as UK times U1, but it's interesting to study the representation theory of UK by itself. And typically, a irreducible representation of UK is given by an k-tuple of integers, lambda, where you specify the order here. So it's a decreasing order, but notice that we don't require any of them, we don't require all of them to be larger than or equal to 0, which is the case for SUK. So this is more general than the Young diagram thing you get for representation of SUK. And this k-tuple of integers is usually called the highest weight of a UK algebra, and the terminology is different from the semi-simple algebra representation theorem. So here are a bunch of examples. First of all, the fundamental defining representation of UK has highest weight the first entry 1 and then 0 all the other places. And its conjugate, the anti-fundamental representation, is given by 0 all over the place with -1 at the last entry. And then you can consider the representation on the exterior power of CK. And this guy has highest weight K1, L1s, and all the other zeros. In particular, this one is interesting. It's called a determinant representation, which is the case where L equals K, and it's labeled by all ones in all places. And finally, the algebra representation of UK is reducible, and it's a tensor product of fundamental and anti-fundamental. So it's CK tensor with CK, and it can be decomposed in this way with a trivial representation and a non-trivial representation. So this is how Gugino transform on the UK. And there are formulas that people develop to compute a bunch of quantities. For example, the dimension of a given irreducible representation of a UK representation lambda can be given by this formula. And also, for our purposes, we're going to have to look for normally free gauge theory. So we have to be able to compute the Casimir operators acting on a particular representation. So the eigenvalues are given by like this, and it's actually very simple to compute these guys. So up to this point, you can write a computer program to scan for all possible anomaly-free 0,2 gauge theories in two-dimension. You can pick any one of them and analyze them. And for our purposes, we'll pick some simple ones of the form like this. So the first example is given by U2 0,2 gauge theory with 4 fundamental chiral superfields phi and 2 chiral superfields in the representation -3, -3. And additionally, we have 5 Fermi superfields lambda in the representation -2, -2. Also, we want to have a 0,2 superposition of the J type of this expression, where f is a degree 5 polynomial of this quantity we call Bij. In terms of physics, it's a barrier constructed by the anti-symmetrizing 2 chiral superfield. Mathematically, this is exactly the local coordinates on the Bruker embedding, where you embed a Grassmannian into a larger projective space. So that's the meaning of this quantity Bij, and we are using a degree 5 polynomial. So this theory is non-free, as you can check. And also the Higgs branch is given by the usual D-term equation, because we don't have any F terms here except for that superposition over there. So this term will give you Grassmannian G24. And the gauge bundle is given by this short exact sequence, as the problem is it's a kernel of this map F, where F is exactly the term inside the superposition. This is exactly what Williams' original proposal applied to this case, where you write down all possible combination of the Kyle's harmonics of fermions and look for the massless guys. And you will see that the massless guys are given by sections of E. All the other guys get mass. So this is how you define gauge bundle in IR. And it works out because -2 plus 5 is 3. And here you can actually see a very interesting phenomenon in 2 dimensions. G24 is special Grassmannian in the sense that it is only Grassmannian that is a hypersurface, a completion section on the Prochor-Manning. Generically, Prochor-Manning will not give you a completed section, but G24 is only one. And as such, it's a degree 2 hypersurface in CP5. So you have a geometry which is a bundle over G24, and G24 is the same as degree 2 hypersurface in CP5. So you wonder if there is a gauge theory describing the second geometry, and the answer is yes. And the idea is that this original U2 gauge theory should be dual to the U1 abelian gauge theory because they have the same Higgs branch. So a technical note is that the bundle 011, which is exactly the determinant bundle, corresponds to 01 on CP5 and restricted to the hypersurface. This is straightforward to say because it's in U1 case the determinant is just 01. And the corresponding gauge bundle defining sequence on this side, abelian gauge theory is given by this. So instead of O minus 2 minus 2, you have O minus 2 and O3. And you have the same degree 5 polynomial exactly over there because the Bij's are homogeneous coordinates on CP5. So you have a non-abelian gauge theory describing a geometry and a abelian gauge theory describing the same geometry. And they should be dual to each other in the sense of suburban two theories of the same IR fixed point. So first thing you should check is that this new U1 gauge theory is truly anomaly free. And by looking at that, you will see that anomaly cancellation in both theories are identical to each other. So if one is anomaly free, the other is anomaly free automatically. And another non-trivial check is that you can compute the elliptic genus of these two theories using the method proposed recently by Bonini and collaborators a couple of years ago. And it's given by the residue of these complicated looking functions, where theta are the Jacobian zeta function, and eta is the eta function. And the residue is computed and sigma equals 0, x equals 1, x 1, x 2 equals 0. This is an index for gauge non-abelian guys, and the abelian guys is a little bit simpler. It's given by this totally different looking expression. If you don't know this business, you may not hope these two expressions will give you the same answer, but it turns out they do. So this is a very non-trivial check that these two guys actually flow to the same IR fixed point. So the duality works out in this case, and it's a duality between a non-abelian theory and an abelian gauge theory.
So the x1 and x2 are associated with the two u1s.
Yeah, they are gauge together, or with U2. And here you only have one x because of U1.
Is there any way in which the u1 of the second guy embeds or is related to some algebra of the u2, or they're just not connected like that?
No. On one hand, you have a non-abelian gauge theory, on the other hand, you have U. Other than that, they have the same Higgs branch. They don't have anything common with each other. So that's a kind of non-interesting example because on Grassmannian is not interesting for heteroscale communication. In string communication, we need Calabi-Yau generically. And here's a simple Calabi-Yau example. So you consider Calabi-Yau hypersurface in G24. The idea is you construct this theory using four fundamental chiral superfields phi, chiral superfield P in this complicated looking representation, and Fermi superfield lambda, and on top of that you add a bunch of Fermi superfields called gamma in this representation. So if you look at the superpotential here, aside from this term that defines the H bundle, you have this additional term which is usual F term defines the hypersurface inside Grassmannian. So these two terms have different purposes. Here again, Bij is a Prochor coordinate, and here capital G is degree 4 polynomial. So the degree works out for W. And you can check the Higgs branch geometry realizes Calabi-Yau degree 4 hypersurface in G24. And the gauge bundle is given by this equation where it's given by the kernel of the map F. Just as before, you have the second term in the superpotential, which defines the short exact sequence that gives the gauge bound as the current. And of course, now you have two factors here, so you have to specify which one goes to which one and how. So the factor 011 goes to O2 by degree 1 polynomial, and the second goes to the second factor with a degree 2 polynomial. So F is a doublet of degree 1 and degree 2 polynomials. Now here again we have an example of abelian and non-abelian duality. So here we have degree 4 hypersurface in G24, and G24 is the same as degree 4 hypersurface in CP5. So you might wonder there's a complete intersection in terms of CP5. And the answer is yes, there is a U1 gauge theory that realizes the complete intersection of degree 2 and degree 4 hypersurface in CP5. And it's exactly the same geometry that we just saw, the degree 4 hypersurface in G24. In terms of this projective space, the gauge bundle is given by the exact sequence like this, with the condition that all these guys are restricted to the hypersurface. So again, you can check. First of all, the anomaly cancellation is if an harmonious condition is one of them is anomaly free, the other is automatically anomaly free. And the second check is elliptic genus computation. For the first non-abelian U2 GLSN, the index is given by the residue of this expression, and the index of the dual U1 gauge theory is given by the residue of that expression. Of course, they look totally different, but turns out the results are the same. And I should emphasize that the reason we can reduce everything to a residue computation is because of what's called Jeffrey-Kerman residue, where there's a prescription you can use to find a contour in a space of gauge invariant operators, and then restrict to that contour and do your integration, and at the end of the day, everything reduced to a residue computation. So again, we have a duality between abelian and non-abelian gauge theories, which is very peculiar in two dimensions.
So is that supposed to be a strong weak duality or what?
No, this is a Seiberg-like duality. It's a Seiberg-like theory. Two theories looking differently in the U way, but they flow to the same IR6 form. So it's not exactly S duality. And let's move on to the analog of Seiberg, exact analog of Seiberg duality in two dimensions. And people have been discovered over the last several years. This is usually called 2,2 Seiberg-like dualities. And the gauge theory data is you consider gauge theory with 2,2 supersymmetry, which is a special case of 0,2 supersymmetry. And you include n chiral superfield in terms of 2,2 chiral superfield in the fundamental representation, and A project for notation here. A here is not A, is an integer. So A number of chiral superfield P in the anti-fundamental representation. And if you write on the determinant equation, there's no F term here, so the determinant equation gives you these two geometries at the two faces where you vary the F parameter from positive infinity to infinity. These are the two possible geometries. And you can look at their differences by interchanging the role played by phi and P. So if you want phi to parameterize the base, then P is going to parameterize the bundle. And vice versa, if P is going to parameterize the base, then the phi will parameterize the bundle. So there are the two phases, geometric phases of this gauge theory. The basic idea we use to analyze duality is to use this mathematical identity. We know that JKN is exactly the same as Jn minus Kn. And you can see this directly from the definition of arithmetics, just interchanging the factors. But under this interchanging of base space, the interpretation of the bundle also changes. So on JKN, the bundle is called S, but the same bundle is called Q star, the dual of the bundle called Q on the other side. And the Q star can be realized by this short exact sequence where I star is the dual of S. So this Q is usually called universal quotient bundle because it's a quotient bundle, it's trigger bundle by S star. But we are not using Q, we are using its dual because it's a kernel. And it's a good thing because we're restricting to the cases where our gauge bundle is a kernel. So Q star is a kernel, so we can realize that in zero comma two gauge theory, or in particular 2 comma 2 gauge theory. So zero gauge theory data that realize this shortly, that sequence. There you have n chiral superfields phi tilde in the fundamental representation, a number of chiral superfields p tilde in the anti-fundamental representation, and n times a number of neutral, gauge neutral chiral superfields gamma and the superpotential of this story. For people who are familiar with cyber duality, this is exactly the same data as cyber duality in 4 dimensions. You have quark, anti-quark to start with, then your magnetic theory has quark, anti-quark, and some neutral meson and a superpotential. So this is exactly the same sort of data that you have in 4-dimensional cyber duality, except this is a 2-dimensional 2 comma 2 supersymmetry. You might wonder whether there's a relationship to cyber duality, and the answer is no. There's no apparent relationship between this and the 4-dimensional cyber duality. The reason we have this is purely geometric. You have that geometric duality, or mathematical identity on top of this slide. But in 4 dimensions, much more complicated. And actually, just by looking at the math result, you can actually do more. For example, the first gauge theory we start with has these 2 phases, and we argue that these 2 spaces are the same. But this guy is described by a different gauge theory as we just discussed. The second gauge theory also has 2 phases, so that's the second phase. And this guy mathematically is the same as this one. And now you have a third gauge theory describing this guy, and this third gauge theory also have 2 phases. Now you can go on and on and on, and there seems to be no end for this business. But how do you interpret that in terms of physics? Because we don't see all these guys. And the answer is that if the number n, the number of chiral superfields phi and number of chiral superfields p, numbers are not the same, then your Fi parameter will have RG flow. When n equals a, Fi parameter does not have RG flow, so you can actually trust your large radius semi-classical argument. But when n is not the same as a, then Fi parameter actually flows. So in some cases, the size of target space actually shrinks if you go to d pi r. In other cases, the geometry actually gets larger. So in the cases where it shrinks, you cannot trust your geometric analysis anymore because the large radius assumption is just wrong. So you cannot use semi-classical argument. So the upshot is that although mathematically we can go on forever like that, in physics, what's meaningful is only the first line, where you have this identity related to 2 guys, where the Fi parameter being large is actually making sense in IR for both of them. For the other guys, for example, if you go over here, Fi parameter actually changes some. So if this guy is expanding, then that's shrinking, so it doesn't make sense anymore. So that's the cyber-black duality in 2 dimensions. And there's more fun games you can play that be discovered by Gary Google from Caltech, what they call the triality. So you start with a 0,2 gauge theory with the following matter content. You have this number of chiral and fermi, and these are the left-moving gauge. Finally, you have a bunch of these guys called omegas, whose purpose is to cancel anomalies. And finally, you have a familiar sort of superpotential like that. You might expect some sort of geometry out of this. And the anomaly cancellation condition sets a relationship on the integers defining this theory. And we will see this condition later again and again. So here, this theory, from our approach, this theory as a gauge theory has 2 phases. The first phase is given by the phi's being the base and the p's being the bond fibers, and similar things for the other guys. So that's the first phase. But you can interchange the role of p and phi. You can get a different base and a different interpretation among them. But mathematically, these are the different spaces. They are just related by the physical gauge theory have different things.
How do you characterize the 2 phases? Or what's the way to do it?
What do
Like
you
a
mean?
physical way to do it?
Physical way, just solve the determinant equation. And the solution is algebraic variety. By solving that algebraic equation, you have the space and the bond.
So it's 2 different branches.
This guy is for Fi parameter being large positive. This guy is for Fi parameter being large negative.
Okay.
So now you have two distinct geometries. So we can do our usual business. We take the second one and transform it into a different expression under mathematical identity. This is a holomorphic identity. The geometries on both sides are exactly the same, but the language is changed. Now you have base GK and the bundle S gets interchanged with Q star as we're familiar with, then the Q star gets swapped with S. So this new geometry better has a UV GRSM description, and it does. It's given by the following data. Because we have Q star, so we also have phi tilde, p tilde, gamma tilde, psi tilde, lambda tilde. You see the pattern is exactly the same as the one you started with swapping a bunch of representation, the numbers, and B and A over and over, and the same superpotential of the same form. This guy realized this geometry on the lower right corner, and then again we do our trick. This guy has two phases. Let's talk about the second phase. Before that, you can check anomaly conversion condition is exactly the same as the one you started with. So look at the second phase. It's given by the swapping the row of P and phi. Again, now you have this geometry. So this the second phase is identical mathematically to a different space, to a different looking space, because they are mathematically the same. So the second phase of the second GLSM has another interpretation as this one mathematically, but we are having a problem because this factor of Q. Q is what's called a universal quotient bundle, and there's no way to realize that bundle in gauge theory. And the reason is actually simple. The moment you add your data to your theory to realize Q as a bundle, you're not actually realizing Q, you're actually increasing the number of dimensions of the square matrix. So it's like in gauge theory, in abelian case where you want to realize this guy, but you cannot do that by the naive adding terms. You're not actually realizing this, you're actually realizing that. So this guy is analogous of Q, so there's no hope to realize Q in terms of gauge theory data. So what do? In our paper, we actually proved one theorem that for 0, 2 nonlinear sigma model with gauge bundle E, the physical spectrum and the physical quantities you can compute are exactly the same as a nonlinear sigma model with a dual bundle E star. So physics doesn't care whether you have a gauge bundle E or it's dual. The physics will be the same. You can check the computational Carroll spectrum, and you can check the origin invariance like indices, and they will always be the same. And this is a non-trivial statement. Now we don't have to look for a theory realized Q. We can look for a theory realized Q star.
Can you tell me how that squares with what you just said?
Oh yeah, to add a fiber like this, naively you would add another Carroll table with charge 1, because this guy is charge 1. But by adding that, you're actually increasing the number of sites by 1.
Right.
So you actually go into this instead of that.
Right. But you're just saying now, with the dual bundle, it would have not happened like that.
Yeah.
But now you're just saying the nonlinear sigma model seems like, I don't know, it seems like there's a nonlinear sigma model with the thing you tried to do.
Yeah.
And it's going to give the same answer as a nonlinear sigma model.
You does have a nonlinear sigma model like this, but there's no GLSM realized. And my argument is that this guy is exactly the same as nonlinear sigma model O minus 1 over here. So this guy can't be realized by gauge theory data. And we're going to do exactly that. And if you go on the pattern like this, start with the first gauge theory, you have two phases. This guy is identically to this, and then you have another phase, and then you do identity plus dualizing appropriate factors of the gauge bundle. You can go to the third GLSM and do it again, you get back to the first one. So this is why you have a triality. You go 3 steps, you go back to your original starting point. So that's our understanding of this triality business proposed by Gary, Gukov, and Putrov from the understanding of this geometry of the Higgs branches, plus this understanding of the physical equivalence of nonlinear models with dual boundaries. So things are nice using just mathematics, but it's not nice enough. And to further test our understanding of triadities, but in general, to propose a mechanism of computing the chiral spectrum of any nonlinear signal model in 2 dimensions with gauge model E. We did the exact computation like that. First of all, the first thing you have to realize is the Fock vacuum of 0,2 gauge nonlinear signal model with gauge model E is not